So I think we should be live now or soon. Go.
All right, I assume we're live now, Ellie. So we'd like to welcome Emily Sutherland to our Faces of Physics speaker series. Before we get started, I want to thank Marshall University, the College of Science, and the Physics Department. They've always been very supportive of our SPS group, our Society of Physics Students. So we're very thankful that they're always welcome for the things that we do and the support that they give us. I really want to thank Ellie White and Jackie Sizemore. They kind of spearheaded putting this together. And they've done a fantastic job throughout the speaker series, organizing monthly talks. Since when did we start this? Almost a year ago, over a year ago now. So it's been going really, really well. So I want to thank the American Institute of Physics for initially sponsoring these talks. And then these are sponsored by the West Virginia Space Grant Consortium right now this fall. So hopefully that sponsorship continues. And we get a couple more talks in for next semester and we continue this. It looks like the new SPS students really want to keep it going too. So if you're interested in what you hear about tonight or have questions, feel free to reach out to our speaker. You can also email the department faculty and staff here in the physics department. And I'm sure we'll be able to answer some questions too about majoring in physics and careers in physics, things like that as well. So Marshall University has around 9,400 undergraduate students and around 2,800 graduate students. So it is a mid-sized university and it is an R2 research university. So if you have an interest in majoring in physics, feel free to reach out to me or anyone else in the physics department and we'll be glad to assist you with any questions that you might have. So within the physics department, we have a BS and a master's degree program. The BS has a few areas of interest. So it has physics, applied physics, biophysics, medical physics, and medical imaging tracks. So there's a wide variety of choices there that allows you to get a BS degree, as well as an area of emphasis sort of tailored to a specific area where you can pick up a minor degree. So I think with that, I'm going to pass it over to Ellie White, and she will properly introduce Emily Sutherland.
All right, thank you, Dr. McBride and Corbin, for the lovely introduction. And thank you to everybody for joining us tonight for this talk. So this will actually be the 11th talk in our Faces of Physics series, and it'll be the last talk that I'll be participating in because I'm actually graduating in a week and a half. So I'm going to be starting a new journey as a data analyst at the Green Bank Observatory. So I am really excited to see how the new organizers like Eli Williamson and others in the club plan to carry out the Faces of Physics kind of tradition. So I wanted to say a huge thanks to all the SPS members and Dr. McBride for their hard work this semester and for all the effort they've put into outreach and getting students involved in physics. I can't wait to see what the club does next. And I'm really grateful for all that they've taught me. So so with that, I'm really looking forward to hearing Emily, our speaker, talk about her experience as a physics/math double major at Marshall, her path into graduate school, and her amazing research. And I'm sure you all are too. So I'll be introducing her here very soon, but first, just a couple quick items to cover. So after the presentation, as always, you'll remember that we'll have a question and answer session at the end, and we welcome you to share your questions via the YouTube live chat, or you can post your questions on Twitter by tagging us with @MUPhysicsClub. If you enjoy this presentation, as always, we hope you'll join us for future talks in the series. Details for the next speaker are to be determined at this time, but we'll keep you posted as soon as more information becomes available. Also, if you missed any of our past events but would like to catch up, please head over to our YouTube channel page and check out the recordings. A lot of great stuff there. All right, so now I'm absolutely delighted to introduce our speaker, Emily Sutherland. Emily Sutherland received her BS degree in 2019 from Marshall University, where she double majored in physics with an area of emphasis on applied physics and applied mathematics. She was in the Marshall University Honors College and served as president for the school's chapter of Society of Physics students. She also worked as an undergraduate teaching assistant for the physics department and as a peer tutor. While at Marshall University, she was inducted into the National Honor Societies for Physics and Mathematics. Her capstone research projects were in the areas of theoretical solid-state physics and numerical partial differential equations. Currently, she is a physics PhD candidate at Worcester Polytechnic Institute. Her dissertation research utilizes computational solid-state physics to model a family of 2D materials known as MXenes. Emily, correct me if I've said that wrong, for applications in clean energy. So for those of you who attend Marshall, especially those in the physics department, you might know that Emily is a bit of a legend in the physics department, and she was president of SPS just starting my degree a few years ago. And she was always one to offer really great advice and support to new students. Emily did a tremendous amount for the physics club and really got it off the ground. So she's really the reason that we're here today, while also acing her classes and doing all kinds of research. So it's amazing to see all that she has accomplished, and we're super lucky to have her joining us this evening. It's my pleasure to hand things over to her now. So thanks again to all of you for coming, and huge thanks to Emily for making the time to talk about your work with us in the midst of your very busy schedule.
Wow, thank you so much. That was such a kind introduction. Yeah, so I'm Emily Sutherland, as introduced, and my goal here is to present my time at Marshall and my time at WPI in a very real sense, because there's a lot that goes into choosing your career and choosing that path, and then the transition from undergraduate to graduate work. It's very different, and the process of it can be very stressful and very intimidating. So my goal is simply to share my experiences, share my path, and hope that some of you can take some advice away from it to aid you in your own path and your own decisions as you traverse this journey yourself. So, of course, the journey to becoming a physicist starts with choosing to become a physicist. I made this choice in my freshman year of high school. I was taking a physical science class, and there was a chapter on geology, a chapter on chemistry, a chapter on genetics, etc., etc. And when I got to the chapter on physics, there was a section on optics, and they explained the process of each individual raindrop acting as a prism and for the white sunlight, and how all of those tiny prisms add up together to show the glorious rainbow that we see across the whole sky. And this was really my first introduction to the incredible symphony of physical processes that conspire to build the observable world around us. And I started wondering, what other everyday phenomena have deeper explanations like this? And what other questions did I not know that I should be asking? And it did not take long for me to determine that studying physics was the way to answer that question. So if memory serves me correctly, within a couple weeks, I was looking at physics programs. And ultimately, I chose Marshall University. At the time, I was planning to be an experimental physicist, which for those of you who know me now may make you laugh a little bit. I know it makes me laugh. But because I was wanting to be an experimental physicist, I chose to major in physics with an area of emphasis on applied physics, which meant taking some I took an engineering class and some computer programming classes, in addition to some more applied electives like optics and electronics. So then in the second semester freshman year, I realized that it would only require about 5 additional classes to add a second major in mathematics. And I'd always thought it sounded really cool if I could say I was a double major. So I was like, why not? And I added my second major in applied mathematics. Then my first summer at Marshall, I had only completed physics 1, but I got the opportunity to work with Dr. Maria Hamilton for the summer, studying the Michelson interferometer. And this was really exciting, especially at that time, because the previous year's Nobel Prize in Physics was awarded for measuring gravitational waves with a very large Michelson interferometer. So this was a really exciting bit of work to get to participate in. I also got to learn a lot about designing and building an experimental apparatus, setting it up, aligning optics, and that whole process of doing some experimental work. And then in the fall semester, sophomore year, I was taking 18 credit hours and I got mono, and it did not get better. And I ended up having to withdraw from the entire semester and go back home to Tennessee and get some medical attention and recover. But during that time, through the process of all those doctor's appointments, it was discovered that I had ADHD. And that explained a lot. And getting treatment for that definitely helped the future times be much smoother and my future classes go well. So that diagnosis is something that I still work through and still work with. I've learned a lot and had some incredibly supportive faculty with that. So then the next summer, I had the opportunity, I applied for an internship at the Air Force Institute of Technology in Dayton, Ohio. And I did not realize it at the time, but found out later that this program had about a 10% acceptance rate. So definitely an exciting project to be a part of. Of course, there's a lot of different projects within that program. The one that I was on was space weather. And so we had a very large data set. I think it was about one data point taken every 15 minutes for 3 years. So a very large data set. And that summer I used MATLAB programming language to write code to process, analyze that data, look for trends, and try and make some connection between the weather that we experience here, particularly thunderstorms, and then the electron layers in the ionosphere of our atmosphere. So this project, I didn't get to do much physics with it, but I learned a lot of data analysis and just research practices, questions to think about, and the approach to take as you're trying to figure things out and look for patterns. Towards the end of that summer, I was invited to continue this project from Marshall. So I worked on it remotely, rewriting basically the same code, but much more efficiently in C++ rather than MATLAB. So I worked on this project until the beginning of my senior year, and I was actually able to count it as 6 hours of honors credits, so kind of worked the system a little bit there. Then that fall, that next academic year, 2017-2018, was when I was SPS president, Society of Physics Students president. And that was a very rewarding experience. I thoroughly enjoyed getting to build things and get experience in the leadership in the academic circles. It was, I guess rewarding is really the best word for it. Rewarding is the best word I have for a lot of my experiences here. So that same year, I also started work as an undergraduate teaching assistant in the physics department. Primarily that was grading homework assignments for the introductory physics class. And then I also started working as a peer tutor for the university tutoring center, where students could make a one-on-one appointment to come for help with their math and physics classes. I also tutored some computer programming in C++ there as well. So then in that academic year, I also got into my more upper level physics classes, started getting into the theoretical classes. And I still didn't really know what research I wanted to do, but I knew I was really enjoying the theory. And partway through Quantum 1, Dr. Nguyen, who was teaching the course, called me into her office and told me that she felt like I was doing a good job in the class and had potential in quantum mechanics, and asked if I was interested in doing my capstone research with her. And I said, of course, that sounds great. So we worked on this purely theoretical solid state physics problem, trying to find the wave functions and energies and behaviors of this quasi-particle called a hybrid exciton in the specific geometry here. My one regret with this project is that I did not work on it as much as I wish I would have. I think I did what a lot of undergraduate students do, and quite frankly, graduate students too. And because there were not hard deadlines, I tended to make it lower priority. And so if I have a lot of advice that I would like to share, but a big piece of advice here, and I tell the students I supervise now, you have to treat research like it's a job. carve out time out of your week that is non-negotiable research time. No matter how busy you are with classes and all the other things, make specific time to get your research done, because you're going to get so much more out of it, you're going to enjoy it more, and it's going to go a lot better for you. But aside from that, I thoroughly enjoyed this project. I learned so much, and Dr. Nguyen was incredible to work with. All right, so then the next fall of my senior year, it was time to prepare my grad school applications. I took the general GRE, which was not too bad. I did not take the SATs, but I'm under the impression that the general GRE and the SAT is fairly similar. If you have a good study book for the general GRE, it'll have all of the math information that you need, all of the tips for acing the essay portion. My biggest recommendation is take a couple months to look at flashcards and study the vocabulary section. That's really the only difficult portion of the general GRE. The physics subject GRE, however, is a different story. It was awful. I hated every minute of studying for it and taking it, and I did not do well. I think it was 100 questions in about 100 minutes, no calculator, equation sheet, and it was anything that might be in an undergraduate physics course. So it was a lot of information to try and study and not nearly enough time to do it justice. But despite not doing well on it, I am here and doing well, so it's fine. And then one of the most challenging parts of the whole process was deciding where to apply. How, there's hundreds of schools. How do you pick which ones to apply to? And I wish I had a better solution. I kind of approached this in a let's apply to all of them kind of way. I started with the list of, I think, top 100 schools in the country and narrowed it down. If they did not have research posted online that I was interested in, I did not apply. If they did not guarantee that I would have a teaching assistantship, I did not apply. If, by the time I had gotten my scores back and such, I could narrow down the ones that I was not qualified, that I knew I would be rejected from. And I also talked to a lot of people, a lot of faculty members, specifically my advisor, Dr. Nguyen, and asked, what schools do you think would be good for me? Where do you recommend that I apply? And I got a lot of insight there. So ultimately, I chose 14 schools to apply to for my PhD. And once I had chosen which ones to apply to, I created an Excel sheet that outlined the school, the application deadline date, if a letter of recommendation had been received by them, if my GRE scores had been received, if I had written my personal statement for them, if they'd gotten my transcript, et cetera, and kept track of all of that on an Excel sheet. And that certainly made the process much easier. That said, each application takes a very long time. Sometimes there are additional essays that you have to write for a particular school, and it takes time. So certainly don't, if you're trying to apply to graduate schools, don't wait to the last minute to work on your applications and get all of this ready. There's plenty of resources online for learning how to write a personal statement and things like that. Also, a lot of the faculty, Dr. McBride, Dr. Nguyen, et cetera, are very helpful if you need advice on how to do these things. Definitely reach out to them and get advice. All right, so then in spring 2019, I had submitted all of my applications by the end of February of 2019, and I was just waiting on responses. And we went to the American Physics Society March meeting for me to present the research that I was doing with Dr. Nguyen. And the whole trip was, quite frankly, a huge adventure that I wish I had time to get more into, but unfortunately I don't. But I think one of the biggest things that happened on this trip was one evening, we had finished at the conference a little bit early. It was a few hours until we were going to go to dinner. And I saw that the Sigma Pi Sigma was hosting a mixer for members. And I had been inducted the previous October. So I decided to go. And while I was there, I got chatting with a group of people about the talk that I had given, the research I was doing, my pursuit of graduate school. And one of the gentlemen in the group gave me his business card and told me that he was the head of the physics department at Worcester Polytechnic Institute, which is about an hour away from where we were at in Boston. And he said that they were still recruiting incoming PhD students for the next year, and asked if I would be interested in coming to campus later in the week and touring campus, meeting some people, etc. And I didn't think much would come of it. But it was exciting. And so I decided, sure, I'll go, I'll see what's going on. And took the commuter rail from Boston to Worcester, came up toward campus, met a few faculty members, a couple people on the graduate committee took me out to lunch and gave me kind of an informal interview, and they invited me to apply. Of course I did. And then throughout the rest of that semester, I also worked on my mathematics capstone project, which was a numerical partial differential equations. So we were using a numerical analysis method to model the wave equation. And the idea here was that we were going to hopefully be able to look at propagation of electromagnetic waves. Unfortunately, we did not get that far in the time that I was there. It turned out to remain a purely mathematical project. But it was really my first big experience of mining useful information from purely numerical results and studying things in terms of this numerical analysis method. So then, as you all know, I got accepted to WPI and decided to come here. And I graduated from Marshall in May of 2019. And then in the summer of 2019, one of the faculty at WPI reached out and asked if I wanted to come up there and in June and July work on a outreach program for Girls Inc., which is a summer program for middle school girls here in Worcester. And so I was really excited to get to spend a couple months working on that. We did a bottle rocket week, and we did an optics week, which was a lot of fun. I was in charge of planning the programming for the optics week. Again, a very rewarding experience, getting to introduce science, especially where optics was what drew me into physics. Getting to share that, with a group of young girls was very enjoyable and very fun. So then my first year, the first academic year there, I started teaching. And typically, WPI has first years teach lab. But I was interested in teaching conferences. And what conferences are at WPI, they're like recitation sections other places. If you're not familiar with that, at WPI, our introductory physics sections will have anywhere between 150 to 200 students in the lecture hall. So the professor gives the lecture, maybe goes over some examples, talks about the concepts, and then the students break into groups of 25 to 50 students, and they go to conference. And the conference instructor goes over problems and helps translate those concepts into solving problems, preparing for their exams, etc. So kind of helping to bridge the gap between lecture and homework. And so I was interested in doing that, more interested than lab. And they knew that I was more interested in theoretical work in general, and that I had had experience both tutoring and grading this material. So ultimately they said, okay, give it a shot. And they scheduled me to start teaching conferences my very first semester, and it went well. I have learned an incredible amount through teaching. I think every term that I teach these courses, I learn something new. And we're on a term system, so I've taught the introductory mechanics conference, I think 5 times now, and electricity and magnetism close to that. And I'm still learning every single time. It's been wonderful working with the students and getting to interact with them and encourage them. And a couple of my students have switched their major to physics, which has just been incredible. As a teacher, nothing is that rewarding. So it's been good. I've also had to teach some labs now and then, which I've not enjoyed nearly as much, but it is what it is. My least favorite part of teaching has been the grading. it's not uncommon about once a term for me to end up with a whole exam to grade, which is the exam for, you know, the 200 students. And I'm pretty sure that like some part of hell just has you grading exams like that. Not sure, but possibly. So it's aside from the grading, it's been a really, really incredible experience teaching these students. WPI has a lot of very smart and motivated students, and it's incredible to watch them grow and learn. So that was kind of teaching my first year. And then I took all of my required core classes my first year as well. So I took my first semester, I took classical mechanics, statistical mechanics, and quantum 1. Classical mechanics kind of picked up where the undergraduate classical mechanics left off from Marshall. We started with Lagrangian and then Hamiltonian, and then went into a lot of like small oscillations, et cetera, as one expects. Statistical mechanics was sort of its own little world. I'm glad I don't have to take it again. We'll leave it at that. I had a really great professor, don't get me wrong, but it's certainly a challenging course and not my forte. Quantum 1 and 2 were definitely my favorites. I had an incredible introduction to quantum at Marshall, 2 semesters with Dr. Nguyen there. And in grad school, the quantum class basically taught the same information, but instead of focusing more on the mathematics of it, like one needs to do in undergrad, we got to focus and go a little bit deeper into the conceptual side of all of it, which was fascinating and gave a really well-rounded picture of quantum mechanics for me. And then electricity and magnetism, another class that I'm glad I never have to take again. Again, had a really, really great introduction, Dr. Vayner at Marshall. I took 2 semesters there, and we went through all of Griffiths, which was fantastic introduction for Jackson. So we, again, went over kind of the same concepts, but now it was learning how to solve them in more advanced ways, different or more involved mathematics, etc. And then this graduate seminar course is just one that that we have to take every semester. It's basically like a weekly colloquium. Sometimes the graduate students will give presentations on their research, etc. It's a 0 credit hour course, but we have to take it every semester. All right, so then my second year, it was a rough year, to be honest, between COVID and everything being online. And then I was also fighting for that whole year, I was fighting a pretty significant chronic pain condition that made everything just more difficult than it would have been otherwise. But with that in mind, I still got some things done. I studied for the qualifying exams. I took them for the first time in August of 2020 and failed them. That's not uncommon. I think it's very, very common, honestly, for students to fail their first attempt at the qualifying exams. It was motivational to study harder the second time, absolutely, because I did not want to have to take them the third time because they are not fun. It was 4 exams. My first time it was 4 days in a row. The second time we had a Thursday, Friday, and then a Monday, Tuesday. One bright side, I guess, from COVID, a silver lining, was that we did take them virtually, and they did give us a little bit more time than they typically do. So they were slightly more relaxed. That said, it's still 4 exams in 4 days, comprehensive, great descriptor for it. So the second time, I had a much better idea of how I needed to study and what I needed to study. So I was able to completely restructure my study strategies and make a much better study schedule, had a better grasp on what I was doing and what it would be like, the expectations, the experience, etc. So the second time I passed. So I took them the second time in January 2020 and luckily passed them. So at that point, there was not a significant transition, nothing changed really, but to PhD candidate rather than PhD student. And then through that time, I continued teaching just the same things. And also through that summer, in the first semester of my second year, I was studying theoretical quantum information. And the idea was that I wanted to go down that path for my dissertation research. However, for a huge variety of reasons, it did not work out. And I learned a whole lot, but I wouldn't say that I really did research in that area. But it was a fascinating topic, and I would like to study it more at some point whenever I actually have some time. And then the second semester of my second year, I had the opportunity to work with an experimental group who was using a terahertz laser to measure water content in paper. And this project was sponsored by the Department of Energy in an attempt to build a smart dryer which would optimize the drying process for paper. Because the paper and pulp industry is like the third leading energy consumer in the United States, and most of that goes into drying the paper. So this effort was part of that collaboration to build the smart dryer. My part in that work was primarily in data processing. So the work that I did at AFIT absolutely came in handy here. My numerical analysis work came in very handy here with taking real data and looking at it, looking for trends, looking for, okay, this doesn't match the model that we expect it to match. What's going on? Is it something in our system? Is it something with our model? And trying to compare and rationalize results compared to a model. It turned out that none of the models we were using were correct because paper is a little funky and water can get both in between the fibers and inside the fibers. So none of the drying models that we were using were correct. But again, I learned a lot. I learned a lot about how to work in a research group, how to work in a structured research environment, and how that process usually looks. And then there was also, so at the end of my second year, I was technically qualified to get my master's in physics. All I would have to do is file a form to get it, but I haven't really seen the point of doing that quite yet. Maybe if I get discouraged, I'll just grab my master's. But you know, partway through the second semester, second year, there was a shift that I started to notice. And the summer between undergrad and grad school, one of my family friends, and someone I respect a whole lot, had told me, you know, as you go through your PhD program, you're becoming exponentially closer to the level of the faculty members. And so there's going to be a shift there from how it was in undergrad. There's going to be more of a camaraderie and a peership versus, you know, being in two different levels, sort of that power chain. And I believed them, of course, but I've definitely seen it and felt it. And it's been a little shocking because I hadn't seen myself, you know, as being even close to that level. And I'm still not. I don't by any means claim that I am. But at the same time, I can feel how much I've grown and how far I've come. And the faculty seem to see it as well. They seem to see me as being competent, which feels huge. It's very encouraging. And it's been really good for my imposter syndrome as well, in just recognizing that maybe I don't see these things in myself, but it's clear that other people are seeing them in me. So the faculty at WPI has been incredibly supportive and kind throughout mental health struggles. My first semester, I did not have any medication for my ADHD or anxiety, and that went rough, but the faculty was so kind and understanding and accommodating where they could be. So certainly, you know, the dynamics of being in your PhD are different than the dynamics of being an undergrad. And it's a really good place to be. I've thoroughly enjoying this point where I get to be sort of an adult in the academic world, but at the same time, I still have people holding my hands and protecting me if I make a mistake. I'm not out there in the big world on my own yet. So I would say that's one of the biggest differences between undergrad and grad school is the classes, and then also just purely the dynamics of it and the expectations for you as a person. So then my third year, which is starting this summer, as I was finishing the research in hydration sensing in the spring, and trying to figure out, okay, what am I going to do next? A faculty member approached me and told me, oh, there's this big MXene collaboration between a few different departments. There's this professor in the chemical engineering department who's doing density functional theory. And I've talked to him about you, and he's really interested in taking you on as a student. Do you think this is something you're interested in, something you might enjoy? And I basically had to say, hang on, let me go Google what density functional theory is. So I did and looked into it and realized that it was exactly what I wanted to do. So I said, okay, let's pursue this. Let's, obviously I don't know exactly what the research is going to entail, but I'm certainly interested in pursuing this. So I signed up and took his molecular modeling course over the summer and realized that it was building directly on my foundations of quantum mechanics, statistical mechanics, electricity, magnetism, etc. And it was a great stepping block from where I was at with my physics degree, even though it was chemical engineering. I think that this field has come easier to me as a physics major than it comes to most chemical engineering majors who don't have that strong quantum mechanics background. So partway through that class, I realized very concretely, I did not know that this field existed, but this is the field I've been looking for. So I've absolutely fallen in love with that research. I've been having a great time. It's going slow because I've still been teaching. But I found out recently, very recently, that after this semester is done, I'll be done teaching for at least 2.5 years. So as rewarding and incredible of an experience as teaching has been, I'm really looking forward to being able to put my focus into this research that I'm so excited about and so passionate about. So I have a couple other classes that I will want to take. I've completed the classes that I have to take. Now it's just about refining my area of expertise and growing in the research that I'm doing. I am at this point working on writing a NSF proposal, style proposal, it's not going to be submitted, but an NSF style proposal for my research, just to show that I can develop those questions and present my research in that sort of way that's going to convince people to invest in it. And once I'm finished writing that proposal, I'll be able to essentially present it, which will be my oral qualifying exams. And after I pass those, the only thing left will be my dissertation and dissertation defense. So it's certainly an exciting time, especially now finding out that I'll be wrapping up with teaching and getting to focus and have more commitment to my research throughout the next couple of years. So with that in mind, I'd like to talk a little bit about my research, and I've tried to not make this too technical so that hopefully those of you who don't have much physics background can still enjoy it, but you may have to bear with me a little bit through some of the lingo. So what is density functional theory? Well, the density part of it comes from electron density. So in quantum mechanics, we talk about the motion of electrons through a molecule. We talk about that in terms of what's called a wave function. And the wave function has no real physical meaning, but from the wave function, we can calculate this electron density. And the electron density does have physical meaning. It's a function that describes the average number of electrons at a given point in space. So the laws of quantum mechanics tell us that we don't get to know the exact location of an electron at any point. But we can know from the way that electrons behave, we can know about how many electrons are likely to be in a given area at a given time. And So if we know about the motion of these electrons and where the electrons are and how they're moving through the material, we can calculate a whole lot of properties of this material. We can talk about it in very comprehensive terms. So that's what electron density is and why it's important. And then the second word is functional. And what's a functional? Well, a function, like x squared, for example, would take in one number and return another. A functional does the same thing, but instead of taking in a value, it takes in a function and then returns a number. So for example, a functional of electron density would be some function. It would take in the function of electron density and then give a number, maybe the energy of the system. So that's what the functional is. And with those two definitions, two scientists, Hohenberg and Kohn, they created and proved these two theorems, which are the foundation of density functional theory. And the first one states that the ground state energy of a system is a unique function of the electron density. What this means is that if we know the electron density, then there will be an energy value which corresponds, and that energy value will be the ground state energy of the system. And there's not going to be any other options for what that energy could be. It's going to be a unique value. And so that's fundamental, that we can calculate the energy of the system in terms of this electron density function. And then the second of the Hohenberg-Kohn theorems states that by minimizing that function of the electron density, by minimizing that, we can find the true ground state electron density, energy, wave functions, etc. So if we minimize this functional, then the electron density function it contains will be the lowest energy state, the ground state electron density. And from that, we can calculate the ground state energy and the ground state wave function. And if we have those pieces of information, again, there's not much that we can't talk about with this system. There's the properties of the system that we can calculate from that information are, I don't want to say infinite because that feels like a stretch, but it would take a long time to reach the limit. So for this reason, density functional theory is the most popular molecular modeling method for especially solid materials. All right, so this one is a little bit more technical. It's the only equation I have here, I promise. So for those of you who are familiar with quantum mechanics, the Cohen-Sham equation states that we can write the Hamiltonian of a mini electron system in terms of kinetic energy, which is energy from electrons moving, a term of potential energy for nuclear or nucleon and electron, nucleus and electron interaction. And then we have an electron-electron interaction term, which is a functional of the density. And then we have this term, which is called an exchange correlation functional. And this term is not known exactly. It's impossible to know what exactly physically that term is. And so density functional theory approximates that term. Depending upon what your system is, there's so many different exchange correlation functionals that you can use. And some of them are better for some applications than others. So depending upon your system and what you're trying to calculate will determine which of those exchange correlation functionals you use. And then we have wave functions here. And then this is the energy of the system in some state. So when you make a calculation with density functional theory, we want to make sure that the result is self-consistent and optimized, minimized, right? So how this works is the program that we use will start by making an initial guess for the wave function based on the geometry of the system, general quantum mechanics, etc. It will make some guess. And then from that guess, it will calculate the electron density function. Once it's calculated the electron density function, we can calculate the electron-electron interaction term and that exchange correlation functional, which are functionals of electron density. once we've calculated those functionals, we can plug them back into this Cohen-Shum equation and calculate the energy and wave function for that system. Now, at that point, we could be done, but we need to check, like I said, to make sure that this is a self-consistent solution, meaning the values, the wave function that we calculate is the same as the wave function that we are inputting. So what we do is we check if the calculated wave function produces the same electron density function that we started with. If it does, great, we're done. If not, it will adjust the electron density function slightly and run through this loop again. And this will repeat until the energy, the calculated energy, is not changing much between loops. And the amount that it changes is dependent on the user. You get to choose that. So essentially, we go around this loop until we make sure that the electron density truly does correspond with the wave function and energy that we're seeing. All right, so like I said, this is a very popular method all across solid state physics and molecular modeling. We are using it to model this family of two-dimensional materials called MXenes. And I'm not going to get too much into the nitty-gritty of what MXenes are. They're called a two-dimensional material because they have this little cell that repeats in two out of three directions. MXenes can have a metal, they have alternating layers of metal atoms, which can be any of these early transition metals. And those layers alternate with what's called an X element, which is either carbon or nitrogen. And these MXene materials result from another type of material called a max phase. The max phase has other layers of, typically it's either from row 13 or 14. And in order to transform this max phase material into a MXene, one has to chemically etch away the additional layers. And in doing that etching, there's a layer of atoms which is left on the two surfaces. And these are called surface terminations. The method of synthesis or the method of etching will determine which surface terminations are left on that surface. Different surface terminations will, of course, change the properties of the material somewhat. And so in this sense, MXenes are very tunable. So, if you need something to be more conducting or less conducting than what you have, you can just look at a different surface termination, for example, or a different metal, or using nitrogen versus carbon, etc. Right, so that's what MXenes are physically. And what are they used for? So MXenes have been studied fairly frequently throughout the last 10 years. And I'm not going to go through all of the applications here, but each of these are applications that MXenes can be used for. A lot in clean energy, catalysis, electronics, gas sensing, et cetera, et cetera. So there's a huge market for developing new devices and applications that use MXenes because they are highly conductive, but they're also extremely stable structures. All right, so when we do a calculation, and I realize I'm cutting short on time here, so I'll try and hurry up a little bit. So when we want to run some calculations on a material, the first thing we have to do is make sure that the geometry is optimized. So we run a geometry optimization calculation first, where we allow the atoms to shift around in a cell of given volume. And so they will shift around until they're in the lowest energy structure possible for that volume. And we can do this for several different volumes and then compare the results. Because nature likes to be at the lowest energy state possible. And so in order for a structure to be stable for an experiment or an application, it needs to be in the lowest energy state possible. So you can see here, for example, this lattice constant of 3.11 angstroms, that gives us the lowest energy for that system, which is the most stable geometry. So then throughout further calculations on that molecule, we would use this most stable geometry and not allow the atoms to shift. One thing that we are particularly interested in is the density of states of materials. And this density of states is essentially a count of how many electrons are in each energy level. So we're kind of looking at the electron density for each particular energy level throughout the system. Now, at the energy equals 0 point here, this is called the Fermi level. And the Fermi level essentially is if there's electrons in or near the Fermi level, they're allowed to move around as they want to. And so the number of electrons in the Fermi level tells us about the conductivity of the material. So for example, we can compare the density of states for a bare MXene with the density of states with some surface termination, and we can qualitatively discuss the impact that that surface termination will have on the conductivity of the MXene. All right, so then band structure here, this one I'm certainly not going to get too technical on. Essentially, each band describes an energy level which is available to an electron. And electrons can only move between different energy levels. So here, this Fermi level at energy equals 0 is of interest again, because if there are bands that are crossing this Fermi level, that tells us that the material is a metal. If there's a small gap around the Fermi level, the material is a semiconductor. And if there's a large gap, it's an insulator. Furthermore, the distance between bands tells us how easily the electrons can move between one energy level to another. In some applications, it becomes very important that an electron can be excited from one energy level to the next higher, and then be kind of moved away so that it does not come back and release that energy. So the band structure helps us to see how likely it is that this electron would recombine to where it started from. All right, and then the third thing here that we are particularly interested in is the work function of these materials. So every material has some place far away from its center where the electric potential goes to 0. And we call this, physically, we call this the 0 energy point. And this is, that comes from, basic electricity and magnetism. When you're infinitely far away, that potential is 0. And so even if the number of that energy level, that vacuum level is what we call it, is not the same for different materials, since physically it represents that E equals 0 point, we can compare then the different Fermi levels of materials by comparing their work functions, which is the difference between the Fermi level and the work, or the vacuum level. So what that work function does is essentially it tells us how likely an electron would be to move from one material to another. So electrons always want to be in the lowest energy state. So if it has a chance to move to a material with a greater work function, meaning a lower Fermi level, it will. And so we can consider MXenes in this case as for use in as catalysts and things like that, where we need to move electrons away from a given point and contain them or store them on their own. All right, so just real quick, the project goals here. So as I mentioned, due to the numerous different types of atoms that can be in MXenes, between the metals, carbon versus nitrogen, and all the different surface terminations, there's a lot of tunability and a lot of customizability for the MXenes. So if you have a specific application that you're interested in, you may want to see which MXene is going to be the best for my application. And so what my group is working on is we're collaborating with data science, experimental physics group, and a synthesis group to be able to identify what are the most important MXenes to be studying right now, and to be able to develop a database that's fairly comprehensive across all of the different MXene possibilities for scientists who are trying to use them in applications to be able to target, find their target properties and locate which MXene is going to be the best for their application. Additionally, we are available to do some consulting work on experimental projects. For example, here, we're working with an experimental group that's working with Department of Defense in using MXenes for gas sensing. And one of the things that they want to do is to see if we attach the silane molecule to the surface of the MXene, how is that going to change the properties? And if we know how the attachment would change the properties, then we could use that as a way to sense if that molecule has been attached or not based on the properties of what we're observing. So my future goal, my career goal here is to do that type of consulting work professionally in the industry, to work in some sort of research lab where there's a lot of different experimental research going on. And I would like to work in a consulting role there where different experimental groups could come. Maybe they're getting some weird results that they don't totally understand, or like this, they need preliminary results for a proposal or something like that. And they could come and ask for help in modeling those and getting their answers. So I know that's a ways away still, and I'm sure it won't be an entry-level position, but that's my ultimate goal with this research and the path that I've been on. So just a few final thoughts, and I'll go through these really quickly. Just a few notes of advice. You don't have to be perfect to be successful. I have failed so many exams. I have, I got a C in physics 1, I got a C in chemistry. Your grades don't have to be perfect. You don't have to be perfect. Your research doesn't have to be perfect in order to be perfectly successful. So don't put too much pressure on yourself there. It's okay if your path doesn't look how you want or imagine. Just keep pushing forward. Specifically with, health problems and, ADHD and et cetera, et cetera, et cetera, et cetera. My path has not been anything like I imagined that it would be when I set out. There's been a lot of times that it's felt like I've been pushed back really far. But ultimately, I look around and I'm right where I wanted to be, right where I hoped to be at this point in my life. And I'm enjoying it. And so even if you're not taking the road you expected to take, that doesn't mean it's not going to lead you where you want to go. The next one is a really big one. Take advantage of as many opportunities as you can, even if they seem irrelevant at the moment. I would say probably about 80% of where I'm at is due to taking advantage of opportunities. Chances that I was given, things that I was offered, that I decided to say yes to, and they turned out to be, even if when I said yes, I was a little skeptical, they turned out to be some of the best things in my path. Don't be afraid to ask for help. No one expects you to know or to learn everything. You, especially going into your doctorate, you are developing an area of expertise. None of the faculty, no scientist that I know of anyhow, has a genuine grasp on more than their area. There's a place where you need to know a little bit of everything. I use quantum mechanics, I use electricity magnetism, I use statistical mechanics, I use programming, I use numerical analysis. I use a lot of different things, but I am by no means an expert on most of them. And that's okay. No one expects me to be any different than that. So the next thing, remind yourself that the successes of others do not diminish yours. It's very tempting to look around you and see other people maybe moving faster or doing things that look more exciting or more fun, or seeming like they're just going further. And that's okay. Science is meant to be a collaboration, not a competition. And so you don't need to be competing with other people. What you are doing is incredible, and you're probably doing better than you feel like you're doing. So rejoice in the accomplishments that you're making, even if they're not the accomplishments that other people are making. Don't procrastinate. Just don't. It'll make your life so much easier if you just don't procrastinate. And then make time for something other than your school and your work. Even if this is watching TV, playing a video game, for me, it's honestly partly my part-time job, which is, I recognize, also work, but it's not school. And it gives me time to step away and think about something other than physics, other than my to-do list. And that's really important, especially if you get into your PhD work and you're working on research. It's a marathon, it's not a sprint. And it's so easy to get burned out so quickly because you have a never-ending to-do list. But you really have to take care of yourself, and I think if you take anything away, that's my biggest advice, is to be true to yourself, take care of yourself, and don't get caught up in how you think things are supposed to be for you. So that's what I had to say. Thank you to the Society of Physics Students for inviting me, and thank you all for joining.
All right, thank you so much, Emily. That was a lovely talk. I know I learned a lot, and Hopefully everybody that was watching did too. So I've been kind of keeping an eye on the chat. It doesn't look like we have any questions yet, but if anybody has any questions for Emily, comments about the talk that you'd like to share, make sure, feel free to post them in the chat or post them on Twitter and tag us. Or if you know me, you can send me an email and I'll read from there. So yeah.
One thing you were talking about was carving out time for your research. So when you were doing your capstone, you said you wish you could have spent more time on it. What advice could you give to a student at Marshall or any other university around the country that has a capstone? How would you tell them to approach it knowing what you know now?
I would definitely say to treat it like a job. And this is something that if you struggle with accountability, talk about this with your advisor too. Tell them that this is what your plan is so that they can hold you accountable to it. But take time, scheduled time in your week, maybe not necessarily every day, but certainly a couple times throughout your week. Schedule time that is non-negotiable for doing research. Whatever else you're doing, when it comes time for that, you drop it and go work on research until that time is up, and then go back to whatever you were working on. I think that's the advice that we give the students. I think I forgot to mention, I have three students that I am supervising for basically their capstones. And that's the advice that we give them, is to treat it like you're going to get fired if you don't do research during those times.
I think that's very good advice, to carve out the time and set the time aside. And another way I've put it is that a student works for 2 semesters at 14 weeks a semester, and they only do 1 day a week, even for a couple hours. I mean, that's less than 30 times they're needing to do research, and that really puts things in perspective. It's really good advice.
My advisor, and I'll comment on this too, and something I'm still working on, but my advisor tells me to do the same thing for writing. He says I need to write for an hour a day from now until I graduate. So also good advice, but I'm still working on putting it into practice because writing's not fun.
Trust me, that is very good advice. So when you're time to put everything together, if you have all your dates, everything organized by date, and just your writing, even if it's not formal, it is so much easier to put things together.
I fully believe that.
So we have got a comment in the chat. It's from Dr. Nguyen. She said, "Hi, Emily. So happy to see you again and proud to see you grow."
Thank you.
So I have a question. Yeah, so you mentioned, how you got interested in physics as a high school student, kind of through the example of, optics and raindrops and stuff like that, which is really cool. So I was curious if, as a younger kid, you ever had any kind of formative experiences with science or anything that kind of, initially piqued your interest that was later kind of reignited in high school?
We did a lot of like field trips, science museums, exploring the world, and learning about all of the different processes and things like that. So certainly there was a lot that kind of primed me for that curiosity and that interest in the world around me. I think that personally, I didn't think too deep into most of it when I was young. Certainly not for lack of opportunity, but just, as I mentioned, I didn't know what questions to ask. I didn't know that there was anything like that going on out there. And, certainly by no fault of my education, I was homeschooled, and my mom did a really great job of making sure that we were introduced to a wide variety of science and history and, arts and everything. I always loved going to like the science museum and things like that. But again, like I said, as much as I loved it and enjoyed it, and I'm sure it was priming me, for this, I didn't think about the little pieces going into all of the big pieces, I guess.
Thanks. Yeah, so I think I don't see any more questions going on in the chat right now. And I haven't got any anywhere else either. So yeah, so I guess thank you again so much, Emily, for doing a wonderful job and for joining us.
Thank you so much for inviting me. I've really enjoyed it.
Yes, thank you for giving a great talk and really good advice for students not only at Marshall here, but for other institutions as well. Really good advice.
It's been a pleasure. I appreciate that.
Great. Well, I'll go ahead and stop the stream now. So good night, everyone, and thank you again for coming. And again, huge thanks to Emily.